In this video, we are going to see another combinational circuit design example. And in this case, we introduce the use of don't cares in a function and how it can help simplifying the solution. So our problem says to design a combinational circuit with four input bits that represent the bits of a BCD digit X. And it has two outputs, Q1, Q0, that should represent the bits of a magnitude Q, where Q is the quotient resulting from dividing X, the number X represented by the input bits, by number 3. Okay, so basically this circuit is a divider that divides BCD digits. BCD means binary code in decimal, so our input bits will represent only decimal digits. It means numbers that go from 0 to 9 only. And the circuit will divide by 3, so if the input represent number 7, it means the input bits represent number 7, so inputs are 0, 1, 1, 1, then the result will be the result of the division, Q equal to 2, okay, the integer part of the result. So if the input is 0, 1, 1, 1, the output will be 1, 0, and so on. So to start, it's good to put it clear what my circuit does by drawing a box and putting all the inputs and outputs of the circuit. In this case, my circuit has two output bits. Okay, it's not bad. It's just very common, but it means that we will have to calculate the logic functions for both outputs. The input is x3, x2, x1, and x0. The output will be q1 and q0. Okay, it's important to remember that all these bits represent a magnitude x, a magnitude composed of these 4 bits, and this output represents a number q, okay, which is the formed by these bits. Sometimes, and it's very common in more complex circuits, we define signals that can have multiple bits, so we have a more compact representation. So this circuit may have also been represented by saying that my input is x, number x, which is composed of 4 bits. So I cross the line here, meaning that it is 4 bits. Normally every bit is named by using a subscript, like in this case. And we could say that my circuit has one output number, Q, which is formed by 2 bits. Okay, this is our equivalent, more compact representation. But basically we have to get used to see the multiple bits sometimes represent a single entity, like a single number, as here. So regarding the implementation, the problem says to use only NAND gates, like in the example we did before. So it means that only NAND gates mean that we have a circuit of 2 levels of gates, first level with NAND, second level also with NAND. This is equivalent to a circuit with the first level of AND gates and a second level of OR gates. And this one I obtained from a normalized expression as a sum of products. So it means that we only need to optimize my circuit for by calculating a minimal sum of product. Okay. So now in order to simplify my circuit, I need to move the information given here to a kernel map. Okay. Some people prefer to write the information in a truth table first. So I will show how to do it, but I will also show you that normally or very often, it's not really necessary to use a truth table first, and it will take some time to do it. But I will comment how could be the process, okay? So if we want to make a precise specification using a truth table, we put the variables here, x3, x2, x1, x0. The order we select here is very important because these bits represent a number. In that order, the first value could be 0, 0, 0, 0, that represents number 0. The next value in the table would be 0, 0, 0, 1, that represents number 1. Okay, so this will be the value of the number x. It's because we use this order in here. If we use a different order like x0, x1, x2, x3, this value would be number 8, not number 1. So it's important to have it into account and to use a sorting of the variables that make it easy to see what they represent. Okay, so my truth table will be something like this. Okay, this is 1, 0, 0. This is number 0, number 1, number 2, number 3. I put here what they represent, and the output will be Q1, Q0. And again, I put this order because the output in this case is the result of the division. 0 divided by 3 is 0. With 2 bits will be 0, 0. 1 divided by 3 is 0 as well. 2 divided by 3 is 0 as well. 3 divided by 3 is 1, which is called like 0, 1. 4 divided by 3 is 0, 1, and so on. So we may go and complete this table. Okay, we'll go right to number 9, for example. That is 1, 0, 0, 1. Then I will press this one. Then we will have number 10, 1, 0, 1, 0, number 11, 1, 0, 1, 1, okay? And we will be completing all the values. For example, 9 divided by 3 is number 3, which is 1, 1. And 10 divided by 3 will give a quotient of 3 as well. But here we have to consider that x is a BCD digit. It means that it will have values up to 9. So these are cases, input combinations, that my variable will not take. If the circuit works properly, it will never take those values. So we will treat those values as don't cares. Okay? It means that I don't care what happened here. It's left in unspecified. Okay? The same thing happened with all the numbers up to 15, the 1, 1, 1, 1. All those are don't cares. We will see how we can use it to simplify my function. And from here, we should go and extract the kernel maps. Okay, we can now, with the truth table, we can go and extract the kernel map for Q1, the kernel map for Q0. Okay, it will be by using a truth table first. It's perfectly fine. But what I want to show you in this exercise, that you can do it like this, but you can directly use the kernel map to start to have the first specification of the circuit. So as an alternative, in general, I have to say that I prefer going directly to the kernel map. Because once it's in the form of the kernel map, it's easier to continue the processing. And actually, the kernel map is just another type of table, very similar to the truth table. I would say it's like a truth table, but with a slightly different ordering. Okay, so I draw my kernel map. And what I'm going to do in this kernel map is that I will put the value of both outputs of the circuit at the same time. So this kernel map will be for Q1 and Q0 as well. Now the variables I will take like this: x3, x2, x1, x0. The sorting is also very important. You can sort the variables as you like, but depending on how you sort the variables, it depends on what min terms you have in your function and what number they represent. So by sorting the variables in this order, the 0, 0, 0, 0, okay, is here, the min term 0 is here, 0, 0, 0, 1 is here, min term 1 is here, and as you see, the min term index is the same than the number represented by the BCD digit. Okay, so it's very good because if you already know what are the min term position here, these numbers is the number of the min term, but also the number represented by the BCD digit. So it will be 8, 9, 10, 11, 12, 13, 14, and 15. So basically we have the same information we have in the truth table. Okay, so note that we are doing this now without using the truth table. And I can calculate the result in basically we divide by 3. This number is 0 divided by 3 will give us 0. I put both outputs at the same position because it is easier at this point to calculate both functions at the same time. 1 divided by 3 gives us 0. 2 divided by 3 gives us 0. This gives a 1. This gives a 1. A 1. 6 divided by 3 is 2. 1, 0, 7 is 2, 8 is 2 as well, 9 is 3, and from here on, all those values are don't cares. Okay, so you have the option to go to the truth table first or go into the kernel map first. You have to write less if you go right to the kernel map. And now from here, we just can separate. If you are going to minimize, you may use different colors to minimize Q1 and Q0 in this map. I do not really recommend it. Okay, so from here we just may go and use a kernel map for each function. Okay, so let me calculate. That's it. So let's make a nice kernel map. I'll use this one for Q1. This is x3, x2, x1, x0. This one is for Q1. Okay. Now let me copy the map. This is the good thing of computer drawing. And we will use this other map for Q0. now just is copied information. I just copy Q1, first number here, this map. These are don't cares. One don't cares. And now I copy Q0. This is 0, 0, 0, 1, 1, 0, 0. All these are don't cares. This is a 0, 1, don't care, and don't care. Okay, now I can start finding the minimal expression as a sum of product. As you remember, because we want a non-end implementation. Now, the good things of don't cares is that I use them if they were ones in order to simplify my prime implicants. Okay, so for example, starting at this one, I have an implicant here. So for me, it's good to consider these are ones as well, to have a bigger prime implicant here. So I consider those don't cares as one. Okay. The same thing happened with this one here. I have this one and this one. I may consider these two as one to have a bigger prime implicant. Okay. And I may also consider all these as ones to have an even bigger prime implicant. Okay. And that's it. That's finished. It's quite big. It helped simplifying the function very much. Okay, but I do it only because it's convenient. I don't really have any obligations to cover the don't cares. Let's see this example. In this case, for example, I have this one here. This is convenient to use these two and these four here. Okay, so it will be a prime implicant. So, and this one can be put together with this first order prime implicant, and with this as well. I have a second order prime implicant here, and there's no, I cannot simplify anymore. And now they see I have this one left that can have this adjacency here, so I can combine with this one. So as long as the don't cares are useful to make more simple implicants, more simple prime implicants, it means bigger groups, I consider they are one, but I don't have to cover them. So for example, there are two remaining don't cares here. I will not consider them to be one because we don't need to cover them. Okay, so the point is that don't cares are not always considered one or are not always considered zero. During the simplification phase, the first phase is find the prime implicants, and so try to find implicants as simple as possible. So in that case, I consider the don't cares one as long as it's good for my simplification. But in the second phase, I don't need to take the these don't cares as well. Okay. Now here, this prime implicant is essential because of this term. Okay, because I have this one here. It is not essential to cover this, because even if I consider it to be one to make it more simple, I don't really need it to be one. So don't care never make a prime implicant to be essential. Okay, this is essential, but for this reason. The same thing happens here. And here, this is essential. This is essential to cover this one. And this is essential to cover this one. Okay. Now, the expressions for my circuit will be Q1 equal to this term here is X3, just X3, and this term here will be X2, X1. And Q0 will be, this term here is X2, x1 complemented plus this term is x3 x0, and this term here and here is x2 complemented x1 x0. Okay, so you see I need the complement of x1, I need the complement of x2. Great. So just to draw my circuit, I need to make two outputs. So I need to build 1, 2, 3, 4, 5 terms. Okay, x3 is just an input, so it's not really a term. Okay, but we will see. 1, 2, 3, 4, 5 terms. 1, 2, 3, 4. So I use 4 NAND gates. And we start to build our terms. Okay, the first one will be x2 x1, the next one is x2 x1 complemented, so I take x2 from here, I take x1 and I use an inverter complemented. The next one is x3 x0, the next one is x2 complemented, I'll take from here. It's going to be a bit messy, but anyway, x2 complemented, x1, I'll take x0 from here, and I'll take x1 from here. Okay, and I have to add all these using another NAND gate. Okay, together with x3. Okay, I have to add x3 to the second level. Now the problem you see that because we are doing NAND, this is x3 alone. Okay, I have to complement x3 to put it in the second level because it's not in a term, so it's skipping the first level and it's skipping the first complement. Okay, as we have already seen. If you are in doubt, you can just write Q1 again by double complementing the expression. So you can see how the operations convert into NAND. So I complement twice. Now I apply only the first complement. Okay, so this is equal to x3 complemented multiplied by x2 x1 complemented, and everything else is complemented. You see, I have a NAND operation here, a NAND operation to do the addition of everything, and I have to complement x3 as well. So I will remove this one because we are doing just Q1, that is the product of just two terms, x2 x1. So I have it here. And this is the product of this term and x3 complemented. It's I'm going to try to make it a bit clear. I'll take A3 through here. It's going to be not optimal, right? Okay, let's do it. Let's do it here. Let's try to draw it here better. Okay, so I have the x3 complement, more or less, okay? So great. Now this is for Q1. Now for Q0, I need three terms. Have another NAND gate, and just in this case, I have no problem. This is the addition of these three terms here. But as you can, this is Q1, this is Q0. Okay, so as you can see, I have done all the terms in the first place, and then from all the terms that I have implemented in the first level, I have do the operation to obtain the output. I have done that because sometimes it may happen that when you have to implement various output functions, there may happen that some terms are shared among the functions, okay? That the two functions may have some equal terms here. So in that case, we don't need to implement the term twice. If I have a term in one expression and in the other expression, I do the term just once, and I can use that term for both functions. So I save some gates, some resources. The same thing happened with the inverters, okay? Here, all the inversions I need to use in one or the other function, but if I need to invert some variable, I may use that inverted variable in the other function. So it's good to do all the terms at the same time and go and draw the circuit of both outputs at the same time so we can share resources if it's possible. It was not possible in this example, but it may be possible in other circuits. Okay, that's all. Thank you.